Welcome back after our hiatus. Okay, so we are getting into chapter 8, which gets into types of chemical bonding. So we will be looking at three basic types of bonding. The first type is going to be ionic bonding, which you're probably most familiar with that style, which is the attraction of two different ions, the electrostatic attraction of different ions to one another. And then covalent bonding, we'll get into covalent bonding, which is elements that rather than one losing an electron, another one gaining, they share the electrons. Some evenly share the electrons, and sometimes an uneven sharing. And then we'll look at metallic bonding and kind of the relationship that metal atoms have with one another in a solid. So let's just get into ionic bonding. So when we look at the energetics of ionic bonding, in the previous chapter we saw that the ionization energy, or the energy to remove an electron, was, in the case for sodium, 495 kilojoules per mole. So then, try to remember that number. So that was 495 kilojoules per mole. So that's how much energy it takes to remove the electron from sodium. And then the other piece of that, so when chlorine gains an electron to fill its outer shell, it gains 349 kilojoules of energy. So if you think of those two numbers, they don't match. The technically, it should be an endothermic reaction, because just calculating with just those two values does not give off excess heat. It would require excess heat. But when we see the reaction, as illustrated in the images there on the left, when sodium metal is put into chlorine gas, it reacts very exothermically, like very violently, produces sodium chloride in the process. So there's some other type of energy present that is thus far unaccounted for. And so we're going to look at that right now. So when you think of, there's another piece, basically. There's another portion of what's holding these things together and what's bringing more energy into this system. And that's the fact that when sodium loses an electron and chlorine gains an electron, they become ions. And rather than, so a sodium atom and a chlorine atom would not be attracted to one another. They're neutral. They have no reason to be attracted to one another. But when they become ions, they then become a positive and negative particle, and therefore become very attracted to each other. And so that is that last piece. It is the electrostatic attraction. It's that positive and negative charge that was newly formed when the electron was lost and gained. That's the third piece. That's that last bit of energy. And we call that energy lattice energy. It's the energy associated with ionic compounds and ionic solids. And when we to calculate or determine lattice energy, we have to completely separate ionic compounds into their gaseous ions. So basically, you put enough energy into that to take it from being a solid to gas form, so where the particles are no longer attracted to each other. And the amount of energy it takes to break that apart is what is referred to as the lattice energy. And it's related to Coulomb. So this is Coulomb's law, and we'll look at this formula in our textbook a bit deeper, because it definitely requires a bit more understanding. But you can find it on page 302 in your textbook if you want to look at it now. And the Q's are in relation to the charge of the entities, or the charge of the different ions. And then D is the distance between their centers, and K is a constant, which is 8.99 times 10 to the 9th joules meters per Coulomb squared. Okay, and we'll explore this equation in class. So when you look at lattice energy, the charges, or the energy required to remove particles from one another, increases as the charge increases. So if you've got a +2 with a -2 compound, so like magnesium oxide and calcium oxide, those are +2 and -2 particles, much more greater lattice energy associated with those compounds. And as it also increases with decreasing size of the ions. So the smaller the ions, the greater the energy, greater the lattice energy, and that has to do with how far away the particles are from each other. So that distance piece between the nuclei of each other. Right, and this diagram, so what you can actually do is you can break down and determine the energy associated with a reaction by kind of accounting for all of it. So by accounting for all three energies, ionization energy, electron affinity, and lattice energy, we can get a good idea of the energetics involved in such a process. So here we've got, so when we talk about like basically looking at these different pieces of energy, and it's going to be a lot easier to talk about it in class than to go over it here. So just kind of take a mental note of that, and we'll take a look at it in class as well. And if you would, you could also take a little bit of time and look at page 304, which has a little kind of closer look on this diagram to better explain it. So I would like you to read that as well before class tomorrow. This phenomenon of greater energy associated with it really defines or explains why the octet rule is so paramount. Because as you get to metals and they lose electrons to get that noble gas configuration, it's because they can't overcome the lattice energy that would have formed by them gaining electrons instead. So it can't be passed. And we will get into this tomorrow, but we'll see you then. We'll see you then.